let us now turn to the so-called ADI method, alternating direction implicit method. We use the difference equation corresponding to the Laplace equation again, and we remember that it took this form. The method is as follows. We put on the left side all unknowns corresponding to the row number G. So let me just point to this row here. So on the left side we put all these unknown, and on the right side we put all the other unknown, which we have colored green. And we are going to we have several such equations for the Dirichlet problem. We have some initial boundary conditions here and here, so we will not consider this equation other than in points, in the interior points where this guy is unknown. So in the ADI method, we consider such equation in all these points, in this point, in this point, in this point, this point, and so on, except on the boundary. So you see here, Ig is the value of u in this point, and I plus 1g is the value in this point to the left of this middle point, and this is I minus 1g to the right of this midpoint. And these two numbers are the values of u on this point and this point respectively. In the method we do as follows. We give all the points now an initial value u called u0, and this is as in the previous method. We can use this, we can put this value arbitrarily. Note just that on the boundary points we have to use the boundary values. They cannot be changed, they cannot be put arbitrarily. Okay, then we decide u index upper index 1, u upper index 2, u upper index 3 iteratively as follows. For every row, for example at number G, we put the equation like this. We put an upper index on all these unknown, which we called on the left side 1 and on the right side 0. So on these 0 points is the starting value, which is arbitrary in all the interior points, except on the boundary where it's given. So we do this and make such an equation in all these points on this row. This gives us several equations, and these equations are particularly easy to solve because they can be represented by so-called three-diagonal matrices. That is matrices where we have non-zero elements on the diagonal and in the nearest points or entries to the diagonal. So these problems turns out to be very simple to solve. So when we have done this, found these points on every search lines, let me just show you. We go through all these rows and compute these values U1. When we have done this, we do exactly the same, but now we are considering columns instead. The left side of the difference equation, we put all the unknowns corresponding to this red column, and on the right side we put the others, and do exactly as we did. But now we have found all these U1 values in the first iteration, and we are seeking for the U2 solutions, and this is found exactly in the same manner. We get one such equation for each point here, interior point, and when we have solved the system of these equations for all such columns, we go back and do exactly the same as we did in the first round. Now we have found all these U2 solutions, and they are put on the right side here, and we replace 1 here by 3. So working with this iteratively, it's possible to show that the solution will converge, or the approximate solution will converge to the exact solution.